In the previous videos we worked towards finding the inverse tan function. In this video we're going to look at generating the inverse sine and the inverse cosine. So that'll be us halfway through generating all of the trigonometric functions we wanted to generate with the CORDIC algorithm. So don't get worried by the mathematics here. We're going to go through the examples on the graphical calculator and you'll see that the actual process is quite simple. So all we've done is written down the CORDIC algorithm again here. So this one here is just the same as the previous page. Now the top one here is going to be given as the inverse sine and the bottom one here is going to be given as the inverse cosine. So this is just the same here, it's just the CORDIC algorithm. Now all we're going to do is change the initialization conditions. And if we change the initialization conditions, then we're going to get a different output. Now you'll notice here there's actually some slight differences here, because whenever we generate the cosine, which is this lot here, the actual CORDIC algorithm changes a little bit because we're going to be comparing not the y values but the x values. So there's a slight change here also in the CORDIC algorithm from this, the sine to the cosine. And again we're going to get our outputs here, and the outputs obviously for the arc cosine is given by this, and the output for the arc sine is given by this here. So let's go ahead and we'll see how we generate both of these in the graphical calculator, and then we'll come back and we'll have a look at the equations. We are going to use the same vectoring mode in order to find the inverse sine and the inverse cosine. Now let's start off by looking at the inverse sine. You've seen this same example previously. Whenever we looked at the inverse tan, we assumed we were given the distances 0.866 and the 0.5, so that is the y and the x, and the y divided by x would be the ratio for the tangent. But now what we have to imagine is we no longer have this x value. The only information we're going to be given is the y value here, which is this height, and the distance here, which is going to be our value r. So in effect we're going to have the y and we're going to have the r. So we're going to have, and we'll have the angle here, so this is going to be the opposite, and we're going to have the hypotenuse. So opposite over the hypotenuse is going to give us the sine. So those are the two bits of information we need, and we're going to be able to work out the angle given both those bits of information. So we're going to be able to work out the inverse sine. Now the best way to understand this is to see it working. We're going to start off with a vector here, which is in pink, and you'll notice the vector just lies along the x-axis. But there is something particular about this vector. It has got a certain length, and that length is a value 0.6072, which is really just the value for our k. Now you'll see why we've scaled it like this just in a moment. Now in order to find the angle here, what we're going to do is we're going to compare the y height of this vector to the y height that we have here, which is going to be our 0.5. So you can see at the moment the y height of this vector is 0. So what we're going to do is we're going to rotate the vector round in the clockwise direction, and then at that point there we're going to then compare again the y height here that we have with the y height of the input information that we have been given. So you can see here at this point we've gone too far. The y height here is greater than the y height here. So in that case then we're going to have to subtract off the next angle. So we subtract off our 26.6, and again we're going to compare the value for our y height, and you can see here the y height is now less than this y height here, so we're going to have to add on the angle, next angle along. So we add the next angle along, and you can see here that the y height is now gone too far, and we're going to have to subtract off in order to get it to the correct position. So we then subtract off this one, and again we're going to continue with this process. So I'll continue with this process, and you'll see us getting closer and closer to the actual value. So we get to this point here, and then this point here, and we see we've gone too far. So we're going to come back, and we've gone too far back the other way. And again, when I say we've gone too far back, we're not comparing the angles, we're just comparing the heights. The height here to the x-axis is less than the height for the input vector, which is the blue vector here. So we then add on again, and we've gone too far, so finally we subtract off. So what we have here after our iterations is an approximation. So in effect this here becomes our approximation, and you can see that the height, the actual height is 0.5 and our height is 0.5001. And again, if we were to add and subtract off the angles as we did previously, then we will get the actual angle, which is 30 degrees, or we'll get an approximation to it. So from the simulation here, it becomes more obvious why we start off with an input vector of length 0.6072. Now we've had to scale this vector back to this size here, because whenever we work through our pseudo rotation, we'll actually have the rotation, and we're going to have also the extension from this point here to this point here. And again, when we work through the next pseudo rotation, it's going to move to this point here, which again is going to be the rotation plus the extension. And again, we do this continuously for each of the iterations. So by choosing the input vector of this length, then we can ensure that we finish up at the correct spot, which is a point which is actually close to the value of 0.5. So finally, we can see that if we're given the value of 0.5 and we're given this length here, now what we can do is we can scale this length here back to the value 0.6072. So if that length there is scaled back to that distance, then we can say in effect this distance here, which is our r, is just the same as the distance that we start off with the vector here. So what we're going to start off with is the 0.5. That's a bit of piece of information that we have, and we also have this distance here which we scale back, which in effect is going to give us a scaling factor. So we've got this height here and this distance here, and when we work through the algorithm we get this angle. So in effect what we've done is we've started off with the y and the r, and we've found the angle. So we've worked out the inverse sine in order to get this angle. So let's look at the mathematics for our inverse sine. We start off with the CORDIC algorithm here, which we've seen previously. Now the only difference is that we're making a comparison here between the value of our y height for our little pink vector, which started off at a height 0, and we're comparing that to the input height. And again, the input height that we were given in that example is a value of 0.5. Now the initialization is going to look like this. We're going to have the original point x0 is just going to be that distance which we said is the value of k, which is 0.607. So in effect this is us scaling the input back to this particular value. And we've seen that here. In this instance here, the value for our an is given by the 1 upon k, or equally 1 upon an is equal to the value of k. Now the initialization for y0 is the value of 0. The initialization for our original angle z0 is a value of 0. And we've got the input value, which just is the value c. In this instance, in the example we've just looked at, the value of c is 0.5. So whenever we work through our algorithm, what we're going to end up with are these values here. So the first one's simple, and the second one here is simple enough. The final value for our y is going to be the value of c. So then in that instance here, the final value for our yn is the value 0.5. Now the value for our xn, well, that's simply given by the simple Pythagoras. It's going to be the length of the value of the hypotenuse, which is given by this term, minus the length of the y value squared, and we take the square root of that. So let's quickly have a look back and we'll see where this comes from in the diagram. I have added in the initialization and the output equations into the simulation. So for the initialization, we have x0 is the value 1 upon an, which is equal to the value for k, which is our 0.607. So this is this vector here. And you can see the value for y0 is the height of this vector, which is the value of 0. And the original angle that we start off is this angle here for this vector again, which is an angle of 0. And the comparison we're making is with the height, which is our yn, which is a value c, which in this case here is going to be the value of our 0.5. So that's the initialization. Whenever we've finished the actual rotation, then we're going to have the outputs that we have here. So let me just quickly work through that rotation. So you can see the values xn and yn. These are the final output positions here of our last vector. So that's the little vector here in pink, which is the approximation to this point. So these are the values xn and the values of our yn. Now you can see that in order to get the value for our output here, which is xn, that's this distance here. Well, this distance here in effect is just going to be the value of our hypotenuse squared minus the y value squared is going to give us the x value squared. So it's just the Pythagoras. So xn is equal to the value here, which is our hypotenuse. So our hypotenuse is going to be anx0 squared, and the y value is simply the value of our height here. In our example, it was a value of 0.5. And the final value for our yn is just the height here, which is just the height 0.5. The angle which we were looking for, theta, is given by Zn, which is the original initialization angle Z0, which is 0 degrees. That was just the original angle of our little pink phaser, which we have rotated round about. And it's going to be plus or minus arc sine of the height here, which is going to be our y, and the length here, which we are given, which is going to be our anx0. And it's plus or minus, and we'll talk about that just in a minute, And finally, the value for an is given by this little equation here, which we've seen previously. So let's have a look and see why this is plus and minus. So if we had a positive value here for our y, then we know that we're going to be in this quadrant here. And if we're in this quadrant, then we're going to have our z0 plus that angle. But if we weren't in this quadrant, and say for example the angle wasn't plus 30, let's say the angle were an angle of minus 30, then the final angle we would get would be our z0 minus the angle that we worked out. So that's how we get our plus and minus. And this plus and minus is just dependent on whether the original value for our y is a positive or a negative value. So I think I'll split this video into two because the video's getting a bit longer than I expected. So what we'll do is we'll cover the inverse cosine in the next video. So just to finish off here, there is one other little thing that happens that we're going to have to take a note of. So if we run through the algorithm, what we're going to have to do is we're going to add on our 45, and you can see the height here is still less than this height. So we add on our next one, and you can see the height here is less than this height. So we add on the next value here, and you can see our height here is still less than this height here. So we add on the next value. But now what's happened is we've gone into this other second quadrant here. And in this second quadrant, whenever we look, because it's in a circle, this drops down again. So this height here, the pink height, is 0.996, and it's less than the height here, which is 0.999. So in effect, rather than work our way back here is what we would want to do, the algorithm is going to look at this and say the height here is less than the height here, so it's going to continue to add on the angle here as opposed to subtract it off, which is what we would really want it to do. So it means that there's going to be in effect a kind of dead zone here which won't operate properly. And we can see that that dead zone occurs for angles which are greater than approximately 81 degrees. So 81 degrees here for this little blue line is going to be a height of 0.9877. And you can see that because of the granularity that we have chosen for the angles, well, at this point here we're going to add on a fixed angle, and that's us added on that fixed angle. But when we add on that fixed angle, you can see that the height here, 0.9865, is actually less than this height. So our algorithm is going to say this height is this height here for the blue line is for the pink line is less than the height for the blue line. So therefore it's going to rotate this round, but it's going to rotate it round in the wrong direction. It's going to add on another angle here as opposed to take the angle off. So that's the reason for the little dead zone. Now there are ways to mitigate this dead zone, but it's beyond the scope of this course and we don't need to get into that in too much detail, but just to note that these little problems do arise. Now the very last thing to note here is that we've only dealt with angles which are within this quadrant and this quadrant here, but of course what we could do is if we had angles within these two quadrants, then we could use just a little bit of trigonometry in order to transpose them into these. So we could transpose the angle in quadrant 2 into an angle in quadrant 1, and we could transpose the angle in a quadrant 3 into the angle in a quadrant 4. But we'll get to that in a different video. That's all there is for this video. I've got into this in a lot more detail than you'll probably find elsewhere on the CORDIC algorithm. In the next video we'll do the same thing, but we'll do it for the cosine function. So thank you for listening. I'll get you on the next video. Goodbye.